Hello and welcome back to the Hutchins School Chemistry Lab. I am Dr. James and today we're looking at our assumed knowledge of carbon chemistry taken from the Physical Sciences course. Let's get to it. Here's an extract from the course document from Physical Sciences. This is the 2018 version of the course, and these are the things that we're going to be looking at in this video. You can pause it right now if you'd like and have a read, but otherwise let's get into it. When it comes to carbon compounds, or hydrocarbons, it's the chain length that determines the first part of the name. I'm calling that the prefix, and what I mean is we're talking about meth, eth, prop, bute, pent, hex, hept, oct, non, dec, undec, or dodec if you're up to 11 or 12. For the course in Physical Sciences, we only went to 10, so the 11 and 12 are unlikely to pop up, but good to know. This presentation is going to have a series of examples, much like this one, and I'm going to leave a sufficient pause for you to press pause on the video and to check that you can name them. So please have a go at naming this first example. This is, of course, butane, based on the 4-carbon chain that's present in our hydrocarbon. As we move on, we need to know a little bit more about naming, so it's the bond order that determines the last part or suffix of the name. The suffix is the end, and it will ring a bell as the ane, ene, or ine. And so we have these 3 examples here. Please go ahead and pause the video and try to name all 3 of them. These are, of course, ethane, ethene, and ethine. With that knowledge under our belt, we move on to cyclic hydrocarbons. When a cyclic hydrocarbon is formed from a straight chain hydrocarbon, we have to remove the 2 hydrogen atoms that allow us to form that cyclic attachment. And as we do that, when we're naming, we add the cyclo prefix to the name. This time we have 3 examples, but we're going to do them one at a time. Here's the first one. This is, of course, cyclohexane. And the next, shown here with a green highlight for the double bond, this must be cyclohexene. And one last one. This is a 5-membered ring, and so this must be cyclopentane. Saturation refers to the presence or absence of a double or triple bond. Saturated means that all bonds are single in the molecule, and unsaturated means that there's at least one non-single bond present. So here's another set of molecules. Have a go at naming them and identifying whether they are saturated or unsaturated. So we have ethane as a saturated hydrocarbon and propene and ethine both present as unsaturated hydrocarbons. We can form hydrocarbons with halogens present. The halogens, fluorine, chlorine, bromine and iodine, can replace hydrogen in hydrocarbons. When this occurs, we change the name to include the halo prefix, so each of those elements becomes fluoro, chloro, bromo or iodo. Halogens are arranged alphabetically in the name. Let's have a go. This is, of course, chloromethane, fluoroethene, and finally we have 2 halogens in the compound. Please note that this I here for iodine is in a font that shows serifs, which are these small marks at the top and bottom of this I to make it distinguished from the L that I've used with a different font for chlorine. So here we have iodine and bromine present. Have a go at naming this bromoiodomethane. In that order specifically because we name the halogens alphabetically. When we start substituting out, we need to identify where substitution has occurred in the name for longer molecules. The previous slide shows a few examples of very short chain molecules, and in each of them there was no need to number because there was no difference between one carbon or the next in terms of numbering. But as things get longer, you need to identify where your functional groups are. Here's 3 examples of different species. Have a go at naming them. These are, of course, chloropentanes, but the first of them is 1 chloropentane, the next is 2 chloropentane, and the final one is 3 chloropentane. Now this middle one is a different example. You might perhaps think this is 4 chloropentane. In this and in all cases, we minimize the numbering, and so here we have 2 chloropentane rather than 4 chloropentane. The chemistry course allows for up to 2 functional groups to be present in a single compound, and sometimes it even goes a little bit cheeky and kicks past that just a smidge into 3 perhaps. We need to be able to roll with the punches that get thrown at us in the exam, and so we need to identify the location and number of each functional group. When we're naming, the functional groups are in order of electronegativity and then alphabetically by functional group. If you're watching this and you've studied phys-sci, electronegativity may not be a fully defined concept for you, but rest assured when you study chemistry, all will be made clear. When we have a repetition of functional groups, we use modifiers, di, tri, tetra, penta, and so on, which is on your information sheet up to the number 10. Here's our first example for you to have a try of naming. With the 2 fluorine atoms, this is of course 1-chloro, 2,2-difluoropropane. Our next example is, following our previous rule, we need to ensure that we minimize the numbering. In this case, we don't have 2,3-dichloro, 1-fluoropropane because that hasn't minimized the numbering. In this case, we number from the other end and we get 1,2-dichloro, 3-fluoropropane. Please also notice, as we're getting to these more complicated examples, anytime you have 2 numbers, they're separated by a comma. Anytime you have a number and a letter, it's separated by a hyphen. And finally, there are no spaces in the names of these molecules. So all 3 of those punctuation rules are important that you follow. We've looked at formulae, and they can be empirical, molecular, semi-structural, or structural. The empirical formula is simply the ratio of elements. It doesn't give us any idea of number. This empirical formula equally describes a molecule that is 200 carbons in length with 400 hydrogens and 100 chlorine atoms. The molecular formula is some multiple of the empirical formula and defines exactly the boundaries of the molecule. We have a molecule here with 4 carbons, 8 hydrogens, and 2 chlorines. But this doesn't define the bonding. The molecular formula only shows the atoms and doesn't show their arrangement. Semi-structural formula, as shown here, gives some indication of bonding by arranging the atoms in the molecule in some semblance of the order that they are bonding with. A structural formula looks like this, and that's what we've been looking at so far in this video. You can see that every single bond is drawn out, and that's the expectation for your course. Let's have a go at naming this molecule. Yes, this is of course 1,3-dichlorobutane. We could arrange this group of atoms in a different way, perhaps into 1,4-dichlorobutane, and that would be called a different isomer. The following compounds all have the chemical formula C4H6Clf. There are many more examples than this. This is just 3 of them. Your job is to name each of them. Here's the first one. This is of course 1-chloro-1-fluorobutanene. The next isomer is shown here, which is of course 1-chloro-3-fluorocyclobutane. Please ensure that you are minimizing the numbers. Chlorine first because of alphabetical order, and the carbon bearing the chlorine must be a number 1 because that minimizes the numbering. Our final option is given here. I'll give you a bit of a hint before I reveal the answer. In alkenes and alkynes, the numbering, if the carbon chain is a little bit different, we need to number to minimize the numbers across the double bond. I'll give you another little second. You can pause and see if you need to make any changes. 3-chloro-1-fluoro-2-methylpropene. This is of course a propene rather than a butane because we've got a methyl substitution going on here. And as I hinted, the double bond changes the numbering scheme, rather than the case for alkanes. We need to minimize the numbering across the double bond. So here we have 3-chloro, still named first because of alphabetical order, 1-fluoro-2-methylpropene. The halogen substitutions will cover the numbering of the alkene, so we don't need to call this a prop-1ene simply because of the numbering allocated by the halogen substitutions. The last section that we looked at in physical sciences are about reactions, and the first reactions we're going to look at are combustion. Hydrocarbons will burn in oxygen if water can be produced as a byproduct. There are 3 options for combustion, and they all involve varying amounts of oxygen availability and result in different products. With complete combustion, we have as much oxygen as can possibly be accessed, and that produces only carbon dioxide and water. Once we start restricting the amount of oxygen that's available, we start changing the chemical composition of the products. Instead of carbon dioxide that we get in complete combustion, we start getting carbon monoxide if the oxygen is somewhat restricted, and we get carbon as a solid soot if oxygen is even more restricted. It's possible to have a range of products, and in a normal fire that you might expect to have at a campfire, you could expect to have all three of these reactions occurring. The oxygen is consumed and produces some carbon dioxide. Once there's a little bit less oxygen, we're going to produce some carbon monoxide, and you'll notice that when things are burning and producing black smoke, that's when we're getting carbon produced. It's not possible to have both carbon dioxide and smoky carbon soot produced at the same time without carbon monoxide being produced. You can have two of them, but you always have to have carbon monoxide present because they're either in the top pair or the bottom pair. If you want to have soot as well as carbon dioxide, then you have to accept that you will have carbon monoxide present as well. If these 9 equivalents of water cannot be produced, then our reaction can't proceed and we are too restricted. Combustion is prevented. The next type of reaction that we looked at is substitution reactions. Now, saturated hydrocarbons, which means that they have no double bonds, will react with halogens with the general formula of X2. The X here stands for either F, Cl, Br, or I, but it's written as an X. X always indicates a halogen. This reaction occurs via substitution. Let's have a look. I'd like you to draw out this substitution reaction and name the products. I'll give you a second and you can pause now. We have a slow reaction that produces 1-bromobutane and hydrogen bromide. The other possible product is 2-bromobutane, which I haven't shown, but is equally possible. If you had butane reacting with bromine in this way, you would expect to produce a mixture of these two things, according to some ratio that gets defined if you happen to study second-year chemistry at university. Unsaturated hydrocarbons will react with hydrogen, halogens, or hydrogen halides, HX, via addition. These are the same halides, fluorine, chlorine, bromine, and iodine, that we were talking about just a second ago. Have a go at this reaction. This is a fast reaction and it only has one product. We have but-1-ene reacting with hydrogen bromide in this case to form 1-bromobutane, or, not shown, 2-bromobutane in the same way as our previous reaction. Notice that hydrogen bromide can react with an alkene, but it can't react with an alkane. Addition reactions will occur not just with halogens, also hydrogen gas and these hydrogen halides. The hydrogen halides are probably the most interesting example, because if we do that, then you can demonstrate your understanding about forming two products, which may in fact be a key aspect of a question that you get asked. So you are expected to be able to identify that two products are formed in a case like this. The final thing that we looked at in the carbon chemistry unit of physical sciences is the bromine test for unsaturation. So using this addition reaction and substitution reaction, the addition reaction being fast and for alkenes and alkynes, and the substitution reaction being slow for alkanes, we can differentiate between a clear, colorless solution if it's a hydrocarbon that's saturated or if it's unsaturated. So in this case, we've got cyclohexene on the left and cyclohexane on the right, and these will react quite differently. Cyclohexene reacts rapidly and decolorizes bromine water to produce a colorless solution. Cyclohexane, on the other hand, will not react rapidly and so will appear to sit and do nothing in the presence of bromine water, and that indicates that that's an alkane and that that's a saturated species. That's about the list of content that we covered in physical sciences. I hope that all made sense, and I'll see you guys next time.